Hi everyone and welcome to this next lecture. This is in the NPTEL course Machine Learning for Core Engineering Disciplines. In today's lecture we will deal with some of the challenges that one can encounter while training neural networks and how we can mitigate these challenges, and these include things like overfitting and underfitting of neural networks, and we have to deal with these problems because neural networks are complicated models, right, and you know that as per the bias variance trade off, right, as the bias decreases the variance increases, and therefore we must try to find an optimally trained model which does well not only on the training set but also on the test set. So let us go ahead and get started. The topic for today is challenges in training neural networks and their mitigation. Okay. So having done in the last several lectures an overview of what neural networks are, how they work, right, how the nodes are connected to each other and how they transmit information, we have a good feel of what it takes to construct a neural network and what its architecture is like, but now we must deal with the various nuanced aspect that someone needs to know to get the best out of neural network models. So one of the first problems that we will discuss here, right, is the issue of overfitting. Right, and this is a problem which we have identified early on in the course, right, and that is why I mentioned a little while ago the issue of the bias variance trade off. Okay. Now due to the large number of parameters in an artificial neural network, in ANNs, right, these models are prone to overfitting. Right, that is, the model works well on the training data but does not work as well on the testing data. Now how do we deal with overfitting, right? We do something known as regularization, and this is something that we have discussed very early on in the course when we talked about ridge regression and lasso, and then later on even in decision trees and support vector machines, regularization was something that was always needed to improve the generalizability of the model and prevent it from not working well on unseen data, right. So even here, right, we will employ, right, regularization strategies to prevent overfitting, right. What does regularization do? Regularization can, right, typically deteriorate training performance. Naturally if you are having penalties on certain terms from being high, you are not finding the most optimal solution, so it can deteriorate training performance, but the hope is that the model, right, will perform well on the test set, right. So typically improves test performance, right, which is the entire aspect about generalization of the model, generalizability. Okay, this is all about regularization. So how do we prevent the overfitting of neural networks? And one strategy, right, which is called early stopping, may have been evident to you from the time when we plotted the train and the validation loss as a function of the number of epochs, right. So the first strategy we will discuss is called early stopping, right. As the name suggests, you stop the training process, right, do not wait for the training loss to saturate, but you actually stop earlier. So early stopping is a regularization strategy that involves halting, stopping the training procedure when the model loss stops reducing on an unseen validation set. This is the key here, right. You are checking the model loss on an unseen validation set, not on the, you of course you are checking it on the training set, but you are simultaneously monitoring the loss on an unseen validation set, and the moment that loss stops reducing, right, you stop the training procedure, right. So this is early stopping, and it is early because it is possible that your training loss could have gone down as the number of epochs increased, but you still decided to stop, right, so that you can get the benefit of increased generalizability. So if you plot the loss versus number of epochs, right, so perhaps your training loss, right, is like this, and it keeps on reducing. So this is training loss, and then your validation loss, let us say it started saturating early on, right. So this is the validation loss. So if you stopped at this point because your validation loss is not reducing, this is early stopping, because your training loss is still falling, but you decided to stop at this point. And I mean, it is possible in some cases that the validation loss can even go up from this point, right. In that case the overfitting is extreme, and certainly we want to avoid those kind of scenarios, right. So in order to write what we just mentioned, early stopping is done because further training would have simply lowered the training loss without contributing to the reduction of the validation loss, right, which is an indicator, right. The validation loss is an indicator of model generalizability. Okay. So what you do is, in practice you do not immediately stop, you wait for a certain epochs, right, and then decide, because it is possible that this plot here of the validation loss may have flattened and then it may start to reduce further, right. So typically you do wait for a few epochs before you call it quits and decide to stop the training based on a saturation of the validation loss, right. So in practice one typically waits a specified number of epochs and this is called patience, right. The number of epochs that one waits is called the patience, right, after the last improvement in validation loss before carrying out early stopping. Okay. So, you do not immediately stop it, but you wait for a few epochs to make sure that the validation loss has really saturated or is going up. So, this parameter patience is actually a model hyperparameter, right, because it affects the training process, right. This one affects not the model architecture, but the training process. Okay. And of course, all these neural network training codes like PyTorch and TensorFlow, they have ways to roll back to the best performing model in case the validation loss starts to increase, right. So, it is usually possible to roll back to a previous epoch if the validation loss starts to deteriorate. Okay. So, this completes our discussion of this particular problem, right, of overfitting, wherein we are using early stopping as a regularization criterion. Okay. So, early stopping is just one of the ways of preventing overfitting, and that is what we have discussed. The next strategy that we will discuss today is called dropout, right. Dropout is another regularization strategy used in ANNs, right, which is designed to prevent the neural network to rely on a subset of model parameters to make its predictions. Okay. So, what you are doing here is that you are dropping out, right, certain nodes during the training process to prevent the network from relying on only a few of the model parameters, right. So, this is akin to in linear regression some of the weights are really going up. So, then the linear regression model only depends on those features to make predictions. Similarly, here, right, it can happen that the weights and biases are such that only a few neurons are active while making the prediction. So, what we do is we randomly sort of drop out some of these nodes to prevent the neural network from just relying on a few nodes and forcing it to sort of activate all the neurons in the network when it is trying to make its prediction. So, this is the concept. How it is implemented is in practice a specified fraction of neurons or nodes, right, and again this is a hyperparameter. What is the fraction of neurons that you are dropping out? These are randomly selected and set to 0 in each forward pass, right. So, whenever you are doing a forward pass to compute the output of the neural network for a given set of features, when you are trying to predict the target variable, you set some of the neurons to 0, right. So, thus each mini batch from the training set uses a different subset of the ANN to make the prediction, right, because you are randomly selecting some of the neurons to 0, right. You are selecting a specified fraction of neurons, selecting them randomly and setting them to 0. That means that every mini batch from the training set uses a different part of the neural network to make the prediction, and therefore you prevent the neural network from relying on only a few of the weights and biases or a few of the neurons, right. I hope this makes sense how dropout is working, right. So, now what is happening here is that you are preventing certain neurons from firing, right, from participating in making the prediction. So, then when you actually do the testing of the neural network, you have to be a little bit careful. You can't just use the parameters that you obtain from the training process right away, because you actually dropped out a fraction of the neuron. So, you have to track, right, how many times the neuron was randomly selected and set to 0. So, this specified fraction becomes very important, right. So, what happens during the production or test run what you do is dropout is turned off, right. You do not really turn off, right, set to 0 some of the nodes, right, that is all neurons are used in the forward pass. Or forward propagation. However, like I said, right, you have to make a small change. Each node's output or each neuron's output is scaled by an appropriate fraction to account for the presence of dropout during the training process. Okay. So, this is sort of the idea of how dropout works. Of course, I am only conveying the concept. If you want to go into more details and also look at the scaling factors, you can of course look at various books, including the deep learning book that was recommended at the start of this course. Okay. So, these are the two strategies we have learned so far, which is basically dropout and early stopping. Now, we will discuss a few more regularization strategies, and a couple of these are very similar to ridge regression and lasso that we looked at many lectures ago. In ridge regression and in lasso, you add either an L2 penalty or an L1 penalty to prevent the weights of the model from becoming too high, and the same thing can be done even here in neural networks. So, the next thing that we will discuss is called L2 regularization, or this is also called weight decay, because you are not allowing the weights to become as large as they could be in case you did not have a penalty, right. So, what this regularization of course does, you already know this, is it penalizes large weights using a penalty in the loss function. So, what happens is that your effective loss function becomes the original loss function, right, whatever loss you had considered, whether it is MAE, MSE or cross entropy loss or so on and so forth, plus a regularization parameter times the sum of all the weights squared in the model, right, and this is very similar to what we did in the case of ridge regression, right. So, this lambda is a regularization parameter. The higher lambda is, the more the penalty is, right. So, the model will the train loss will come down, the train loss will go up, but hopefully the test loss or the validation loss should come down, the generalizability should improve, and this is of course the vector of all weights, or just these are all the weights in the model. Okay. So, I hope this makes sense, given that you already know all about ridge regression and this kind of a regularization term. The next strategy which is used is of course very similar to lasso, and this is the L1 regularization strategy, and here instead of the sum of squared weights, we just take the sum of the absolute values of the weights, and thereby we penalize very large weights. So, the loss here becomes the original loss plus the regularization parameter times the summation of the absolute value of the weights, right. So, these are again the weights, and then this is a regularization parameter. So, what that means is that if you have high lambda, then your training loss will go up, right, but expect the validation loss to come down, and of course, if lambda is equal to 0, this is the neural network ANN without regularization, and this should give the best training loss metric. So, the lowest training loss will be obtained if you turned off the regularization. Okay. Now, again there is a slight difference between a regularization with an L2 approach and with L1 approach. You already know that in the case of the L1 regularization, which is used in lasso, some of the weights can actually become 0, and thus the L1 regularization encourages sparse weights, right. Some of the weights can become 0. So, that means there are fewer non-zero weights. So, these are called sparse weights by forcing some of them to 0, right, just like what happened in the lasso model, right, the least absolute shrinkage and selection model, and this is useful, right, during model compression, right. If you want to compress a model, right, by excluding some of the weights, then this is the way to do it, or if you are interested in feature selection. Okay. So, that is all about the regularization strategies based on adding penalties to the loss function. We also have a few other types of regularization. One of them is particularly useful when we are talking about images or data which sort of can come in different forms and varieties. You can have rotated images, you can have images with noise and so on. So in these cases what you can do is something called data augmentation. So what is data augmentation? In this case you apply some random transformations right to help the model generalize better across variations in the data. Okay. So for example with images, right, operations like rotation, right, a rotation should not impact what is inside an image, cropping an image such that the major part of what you want to focus on, if you have an X-ray, let us say the part in which the X-ray is there is not cropped, or if you are focusing on an animal, the part in which the animal is there is not removed. So that should not change the output of the model. So cropping, zooming in, resizing, etc. So you can carry out randomly combinations of these operations and then you can add the data, right, you can augment or increase the number of data points, and this will help the model generalize better, because now it will know that even if you rotate the image or you crop it slightly or you zoom in slightly, it is really the same image, and that is particularly useful in the case of applying convolutional neural networks to images. Now in a similar vein, purposeful noise injection can also be done. So let us say you want the model to be less sensitive to noise. So purposely you can add noise. So if you have an image, you can basically set some pixels to 0 or you can change them slightly, and this is also very useful, right, to help the model generalize better, right. So these are the 5 strategies that we have discussed today to deal with the problem of overfitting with neural networks. These include data augmentation, L1 and L2 regularization, dropout, as well as early stopping, right. So with the discussion complete on overfitting, let us move on to another problem that one can encounter when we are training large and deep neural networks, and this also becomes evident in recurrent neural networks. So this problem is called the vanishing gradient problem. So in this problem, right, what happens is gradients of the loss function with respect to parameters and these, as you know, include both weights and biases, appearing earlier on in the network. So earlier layers is basically closer to the input layer, become smaller and smaller. Right. So this contributes to the name vanishing gradient, right, because the gradients of the loss function with respect to the weights and biases in the earlier layers become smaller and smaller, right. So now this is a problem, right. Why? Because if you remember, right. How are the weights updated? They are updated based on the some variant of the steepest descent or the gradient descent method, wherein you update the weight as W minus the learning rate times the gradient of the loss function with respect to the parameter, or the partial derivative of the loss function with respect to the parameter. This is the learning rate. Now if your gradient basically vanishes, right, if this is approximately 0, then W does not change, right, or changes very minimally, right. So this means that the parameters in earlier layers hardly change and are effectively frozen in deep neural networks. Okay, so this is a problem, and you can easily see why this happens, right. So let us just take the example of your sigmoid activation function. So here g of z is the activation function, that is 1 over 1 plus e to the minus z, right. Now as we have seen in the back propagation, you repeatedly take derivatives, right, of various functions, and you also had the derivative of the activation function appearing there. So if you computed the derivative of the sigmoid activation by chain rule, it will be minus 1 divided by 1 plus e to the minus z whole square times the derivative of 1 plus e to the minus z, which is basically minus e to the minus z. So this derivative is essentially e to the z divided by 1 plus e to the minus z, which you can actually write as 1 divided by 1 plus this squared. So which you can write as 1 divided by 1 plus e to the minus z times 1 minus 1 divided by 1 plus e to the minus z. Okay. The reason for writing this will become obvious in a moment. So this is essentially your g of z, and this is 1 minus g of z. Okay. So your g dash z is basically g of z times 1 minus gz for sigmoid activation. Okay. So now what is the problem here? Now we know that your gz, it lies between 0 and 1, right. You have 1 over 1 plus e to the minus z. So this lies between 0 and 1, right. So it becomes 1 when z is equal to minus infinity, and then it becomes 0 if it becomes 0 if z is minus infinity, and it becomes 1 if z is infinity, right. So we know that gz lies in this range. So gz times 1 minus gz, right, that will have a maximum actually at 0.25, right. So since gz lies between 0 and 1, the maximum value of g dash z, which is g times z times 1 minus g times gz, is actually 0.25, and that will be when this number is 0.5 and this number is also 0.5. So then you will get 0.25. So that is the maximum value of g dash z. Of course you could have differentiated this whole expression and also proved that this is 0.25, but writing g dash z in this nice form is an easy way of saying seeing that the maximum value is 0.25. Now if you have several of these derivatives, right, and all of them are less than 0.25, what will happen, right, this 0.25 will get exponentiated by, let us say, capital N, right, and this is the number of layers, for example, and this will slowly tend to 0, right, when n is large. this is the number of layers. So, you can see how the use of a sigmoid activation function can lead to the vanishing gradient problem, because multiplying several such small values will keep on reducing the value of the derivative. Okay, so that is the problem, right, if you are using a sigmoid kind of a function. Okay. So, what is the solution to this problem, right? The solution to this problem, to avoid vanishing gradients, is to use a different kind of an activation function, for example a ReLU loss function, right. So, if you use the rectified linear unit, so if you use the rectified linear unit activation function, right, and if you remember, this is essentially max of 0 comma z, which is essentially 0 if z is less than 0 and it is z if z is greater than or equal to 0. So, the derivative of gz is either 0 or 1, right, and if you multiply ones again and again and again, right. So, where all the neurons are active, then you will not get the vanishing gradient problem, right. So, thus avoiding the vanishing gradient problem. Okay. And this is because, right, the derivatives will not diminish if repeatedly multiplied, right. So, the solution is to use the ReLU activation function instead of sigmoid and tanh if you are encountering the vanishing gradient problem. The other aspect here is that of a recurrent neural network, because in a recurrent neural network it is like a loop, right. The output of the previous iteration is sent to the next iteration along with the updated value of the features. This is also a problem there. So, for recurrent neural networks, RNNs, vanishing gradients can also occur, right, over long sequences, and to avoid this, right, different variants of RNNs have been developed. So, these include the gated recurrent unit, which is a GRU, or a long short term memory, which is an abbreviated as an LSTM. Okay. So, with this we come to the end of this particular lecture, wherein we discussed various problems that can occur when we are training complex models like neural networks, and these can include the problems of overfitting or vanishing gradients or even exploding gradients. The exploding gradients problem is something that we will discuss in the next lecture. It is also something that needs to be alleviated, and then we will move on to other examples of neural networks and trying to understand where these are applied. So I hope you learnt about mitigating the challenges encountered while training neural networks today, whether it is by dropout, whether it is by early stopping or L1 or L2 regularization, and I hope you will employ some of these in your own research. Thank you for joining and see you next time.